This is the last video in our gas law video series here, and this is on Gay-Lussac's gas law here. We are talking about it conceptually today in class, and we'll get to it mathematically this week. Again, just like with Boyle's and Charles' law, you need to be able to not only conceptually understand the law, but you need to also be able to mathematically solve these laws. The conceptual understanding of this is that Gay-Lussac's law is a direct relationship between pressure and temperature. And so just like with Charles' law being a direct law here, both variables are either going to increase or decrease. So for Gay-Lussac, this means that temperature increases, so does pressure, or if temperature decreases, pressure also decreases. Examples of Gay-Lussac's law in the real world is if you've ever seen a pressure cooker, where you increase the pressure on the cooking utensil, and as a result the temperature inside is higher than what it would normally be. So you may see this for like fried chicken. They cook it in a pressure cooker so it cooks faster. Tire pressure between summer and winter is also due to Gay-Lussac's law here, and also the movement of the piston in your car engine. As you increase temperature, you're increasing the pressure inside, and so something's eventually got to give. Okay. The math for Gay-Lussac's gas law here is that it's pressure 1 divided by temperature 1 equals pressure 2 divided by temperature 2. Now, just like with Charles' law here, we don't want any negative temperatures, so you have to convert temperatures that are given in Celsius into Kelvin. So the shorthand for this problem is P1 divided by T1 equals P2 divided by T2. Pay attention to this. This is the difference between Gay-Lussac and Charles' law. Charles has to deal with volume. Gay-Lussac has to do with pressure. That's the only difference between these two formulas. So if we look at our example for tonight, a pressure cooker is sealed at 3.58 kilopascals at a temperature of 308 degrees Kelvin. What is the pressure at 350 Kelvin? So I'm going to start by going in and identifying the parts of the problem I know. So I know my P1 and I know my T1. So, and then we also know our T2. We are looking for P2. Okay. And so if I copy over my formula here, we've got P1 divided by T1 equals P2 divided by T2. And I plug in what I know so far, which is that I have 3.58 kilopascals divided by 308 Kelvin is equal to an unknown pressure divided by 350 degrees Kelvin. Okay. So when we go to solve for x, this is going to be 3.58 times 350 divided by 308 to isolate the variable, and that's going to give us a final answer of 4.068 kilopascals. Oops. Okay. And again, just like before, we can check our math here and see if this makes sense. So looking at the problem, I'm seeing an increase in temperature. So if I have an increase in temperature, this means that my pressure has to increase. So if I got a smaller pressure for my final answer, I know I've made a math mistake. And we look at this, 4.068 kilopascals is larger than 3.58 kilopascals. So I'm going to assume that my math is correct. This makes sense. And that's how you do a Gay-Lussac related problem.